Okay, so thank you very much, Jean-Pascal, for the opportunity to talk in this workshop, and thank you to the other speakers so far. It was very interesting, eye-opening work. I'm going to talk about two pieces of work, mainly the first one, which is about inferring EI circuitry from microscopic data. This is work done by my PhD student, Alexandre René, who's co-supervised by Jacob Macker, who's now just moved to Tübingen. And that work is coming out next month. And also, relatedly, although these projects were done independently, started independently, now they're starting to collide, is how do you understand gamma and beta bursts? What dynamical regime are you talking about? The quasi-cycles, and how can you characterize the statistics? And for this work, you need a good model you can infer from the data. That work is from my PhD student, Arthur Pawanwe, which came out last year. Okay, so I'm gonna start with a motivation from here and then go to one and then come back here if I have a little bit of time at the end. So a typical motivation for inferring network circuitry is to understand the origin of brain rhythms. So these are ongoing voltage fluctuations, which would, can be LFPs or EEGs in different frequency bands, gamma or beta. And we've heard that, they play major roles in communication between areas of the brain, memory, attention, motor control. And of interest for this talk in particular is the rhythm statistics, fluctuations in these rhythms. And these statistics can be related to brain disorders such as Parkinson's and epilepsy. So here's an example of gamma bursts, just to give you an idea of the stochasticity of brain rhythms. This is data from Zing's lab. So you have an awake macaque, and you have these LFP fluctuations, and you have the spectrogram underneath, and you see these epochs where the amplitude of the, or the power in the gamma band is higher, and other times where it's low. So you have these bursts of gamma activity. So, gamma is not a nice sine wave going on in the brain. It just comes and goes and starts and fits seemingly randomly. Here's an example from André lab on beta bursts in monkey motor cortex, where you get the same kind of pattern where you get these bursts that get suppressed when we're about to do a movement. And disorders in these burst statistics, will be related to pathology. So we were looking for a general framework to understand these burst dynamics. But in order to do that, you need some model with E and I cells. And we know there's been various candidate models for rhythms, such as inhibitory only cells, E and I cells, other variants for slow fast models or nested rhythms. And the question often arises, is it an autonomous rhythm, or is it induced or altered by stimulation? Much of the modeling is deterministic, but real rhythms are stochastic. And by stochastic, I don't mean chaotic. There's lots of chaotic stuff going on as well, but there's lots of high dimensional noise as well. And so the question is, can we infer network mechanisms from the data? Here's an example where, the burst durations that I just showed you have a distribution, and they have a distribution of frequencies within them. So what does this distribution of burst durations depend on? As a typical example we've been looking at in my lab. So you'll come up with, your favorite model, such as a stochastic Wilson-Cowan model, for two variables, two populations, state-dependent noise, and so on. But, what are the parameters in here? There's two noises. How do you deal with this? What is it, an EI network, or is it an II network? If it's asynchronous activity, are you near or past the boundary for synchrony? In some cases, there's more and more evidence that a lot of these dynamics are actually, if you turn off the noise, it's just a fixed point. There's nothing interesting. It's all induced by noise. So this is work also in Rafael Bogat's group for beta oscillations, and Zing, and we've shown it also in EI networks for gamma. So how do you infer when the noise is really a good part of the dynamics? So what are the parameters, and does the model even make sense? So let's that was an introduction, a motivation for the work on the inference, so mesoscopic population model activity. So you have microscopic data, for example, spike times, or they can be calcium signals from different cells in different populations. And you use these microscopic data to construct population responses. We call that the mesoscopic level. Simplest thing is you just add them up and you create some mean population activity. Then you need some kind of theory that links mesoscopic to microscopic. And of course, there's tons of work in this, at this effort. But if you have a theory that can link the mesoscopic to the microscopic, then why not just try and infer the mesoscopic theory and from the data? And now then you can use that theory to go back to the microscopic. So the goal here is going to be to infer the mesoscopic dynamics. You will need to have a likelihood. So you have to be able to estimate a likelihood from observed activities. So that's why it's a good idea to have some stochasticity, but that comes for free in a lot of applications. Now we're going to do a maximum likelihood fit. That's actually going to be map estimates to find the mesoscopic model parameters. And you can include adaptation or other phenomena of interest if you know this micro to meso theory exists. So you need a theory. So the point is that you're really putting in some neural dynamics into the picture and trying to infer this neural dynamics, but not at the microscopic level, but at the mesoscopic level. Here's a picture of what it is. You have a microscopic model. You just simulate thousands of neurons. In our case here, there's going to be adaptation. There's going to be E and I cells, and there's going to be an escape noise. So like a hazard rate. So you can simulate these and get your raster plots. You can sum these up and you get these network population activities for the E cells and the I cells. From the microscopic model, you can do theory to get the mesoscopic description. For example, in terms of 2 E populations and 2 I populations, and you have all the connectivities between them, the membrane time constants, and then you want to use this and this together in an iterative manner to estimate the parameters. All right. Now the modeling choices are guided by typical considerations. Your model should be rich enough to describe the phenomenon of interest. The model must quantitatively connect the dynamics to the observations. And within 1 and 2 here, you're going to try and choose the simpler models. There's some Occam's razor argument. The models are divided into 3 parts. You'll have a model for the input, a model for the intrinsic dynamics, which is coupled to the input, and you'll have an observation model, which is coupled to the dynamics. And 1 or more of these parts can be stochastic. This is not a simple model, okay, but it's actually a really interesting model. And it has, so it's by Thilo Schwalger et al. Came out a few years ago. That we decided to choose because it had a lot of the features that we wanted. And I'm just going to draw your attention to 4 zones here. There's like some input dynamics. And then when the cells fire, they become refractory. When that refractory period wears off, they become free. And then there's this complicated algorithm to take into account finite size effects. So the stochasticity comes from the finite size. So there's noise at this level and noise in the hazard rate functions. In the end, you're generating these variables, which are amounts of spikes generated by the population at every time step, which is going to be a binomial. Let me give you just a summary of what this model does, Schwalger's model. So you have spike trains, you have synaptic responses, which are exponential kernels here. The synaptic input is going to be the convolution of the 2. And you have dynamics. So this is a generalized integrate-and-fire. So you have leakiness, you have external inputs and synaptic inputs. And the threshold also goes up every time the neuron fires. So lots of neurons have this property that, threshold adaptation or current adaptation after a spike. And then you have a hazard rate, which you throw the dice, at every time step to see what's the probability of firing, which is a function of the distance between the voltage and this time fluctuating threshold. Okay. Now, so in this model, you have, time is K, population is alpha. So you'll have an expected number of spikes in a given time bin. You'll have a single neuron firing probability. You'll have numbers of neurons firing in a given time step, which is going to be a binomial with this probability. This probability is this, and this depends on this hazard rate, which depends on voltage and threshold. So it's quite complicated. Okay. And in the end, what we do is we write a likelihood out of all this. So for a data sequence of length L, finite history S, so there's a quasi-renewal hypothesis going on here for those of you who know what that means. Starting at time K0, you can write down what's the probability of your sequence, like we've just seen in Ankyu's talk. You just multiply it out over the populations and over time. You can write down these probabilities of observing these numbers of firings per time bin given the history. So you're including some of the history of the population in there. The likelihood will be written down as with binomial stats. And then you're going to write down you're going to look for the maximum a posteriori, so a map estimate of parameters using your favorite tools, such as stochastic gradient descent on the posterior. If you're doing map, you have to have some priors, and we're using non-informative priors that still help constrain the trajectories to more realistic areas of parameter space. So I'm going to show you examples from 2 populations and 4 populations. You're going to have, for example, a 2-population model. You're not going to estimate all the parameters. Some of you have a good idea of, some are redundant, but for example, you'll estimate membrane time constants, connection weights, escape rate at the threshold, noise level, synaptic time constant, adaptation strength, adaptation time constant. And there's another example I'll show you at the end, which we tried to see how much it scales to a more complicated model. Here is how it works. You'll use, for example, an input, which is a sine wave modulated noise. And you'll train the network with this, and you'll do your learning. And you'll have your activities down here and your rasters. So the inference algorithm only sees the summed activity. It doesn't see the individual firings. And you run 25 fits, for example. You keep the one with the highest likelihood, as these authors have suggested is a good, efficient way to proceed. And here's an example. You're looking for the connectivity between from E cells to I cells. And here are the 25 fits. And you'll see that there's some of them go off in crazy directions, but some of them are going to converge around this black and red curve. Now the black curve is the meso model ground truth obtained from the micro model ground truth. So you have a micro model which has the parameters, and you plug those in the theory and you get the meso parameters. So they're converging to the meso parameters. Well, in this case, they're very close to both ground truths are very close. So you do this, and then you repeat a number of times to try and get your best estimates. Then you can use what you obtain to see if the model can generalize. You can then, instead of applying a sine wave, you can put low-pass filter noise, like a frozen noise input. And here what's plotted is the true micro in green. It's maybe more visible out here. True micro and some fluctuation zoom here. And then your theory meso is in orange. And the inferred meso is in blue. So actually the model, the inferred model, is doing pretty well at estimating the activity of the model. And you can write down parameters such as trial averaged, Pearson correlation coefficient between these two things, or the root mean square error, whatever you prefer. They have slight different advantages. You can calculate the spectra to see if they stick to the data. The spectra are doing a good job as well. And you can get a convergence in about 20,000 spikes, which is about 9 seconds with the parameters of this model. So if you go from the top curve to the bottom curve, you see that the green is matching the gray better than the yellow is matching the gray. So as a function of data length, you'll get an increase in your correlation coefficient between the frozen noise and the activity of the model. So the root mean square error is going to go down. So with fairly limited data, you can actually do a fairly good job for this two population model. Here's an example of an interesting picture you can get from this approach. So of course, the whole, I didn't mention it, but the whole modeling effort to go from micro to meso assumed homogeneous populations. Now, that of course is not reality. So what if you have an inhomogeneous or heterogeneous population? So what we've done here is we've taken 3 time constants, the membrane time constants for the E cells, the I cells, and for the adaptation time scale. And we've given them log normal distributions. So the microscopic, when you take these parameters and you measure the microscopic activity, you'll see these kinds of curves. So the idea is which one, so then you want to see how well the model can perform in the presence of this heterogeneity. So if you just take the mean of these parameters, which, by the way, is not a good idea if you have log normal distributed parameters, but if you just take the mean, which is the standard reflex, you're going to kind of overshoot quite a bit, and the error is going to be, relatively large, 5.84. If you infer only these 3 parameters, pinning all the other ones to the ground truth, you do better. But actually, if you infer all the parameters at the same time, you do even better. So the moral of this story is that fitting more parameters, like all 14 parameters rather than just the 3 that were heterogeneous, it takes more time, but it gives you more opportunities to accommodate the mismatch between the model and the data. Okay, so here's another picture of this, of the results. So we're using Bayesian inference to get the best fits, but this also allows you to characterize a parameter uncertainty and also the correlations between parameters. So the uncertainty is going to be, a function of how wide the distributions are from the map estimates. But to get these correlations, we use Hamiltonian Monte Carlo sampling to generate the 14-dimensional posterior. Then we can look at these marginals. So we integrate out, for 12 dimensions and keep 2. And then you can see, for example, that, and then these are just ellipses fitted, assuming Gaussianity. So in some cases, the ellipses are fairly round if you're looking at correlations between 2 parameters, but for other ones, they're quite slanted. So in fact, if you looked at this one up here and this one down here, well, these are connectivities onto the same population. So you actually see strong anti-correlation between connectivity pairs impinging on the same population. That comes out of the fitting, which may be an interesting property to investigate in the model, in the data. Here are other few parameters, and now you see some very tight correlations between certain parameters, like the adaptation strength, J, and the adaptation timescale, tau. You'll see very strong correlations, which suggests that actually there's just a linear relationship between these 2 things, and it's not, you don't need to fit both of them, you can just fit the ratio and save time. And now we've looked at how to extend this to a more complicated model. So this is the model of Pochance and Diesman for layers 2, 3, and 4 in cortex. So the network is not just 2, like 1 E and 1 I population, but you have like 4. The training, in this case, we did by adding sine waves only on layer 4. But it turns out that the fluctuations going on native to the model is enough to allow layer 2 and 3 cells to explore their phase space and therefore allow the model, the fitting algorithm, to explore more of the parameter space. And you can get fairly good responses to the data, even if you have 36 free parameters. It takes a while, but you can do it. Okay, so conclusion of this part is, we can infer mesoscopic dynamics from microscopic data. I didn't show you the mesoscopic equations because it takes too long. But you can maybe get some other favorite model of yours that links microscopic to mesoscopic. It might be less complicated than this one, but as long as you have a stochastic feature to it that allows you to formulate a likelihood on which you can do the work. The usual caveats is that, what if the model is incorrect? Well, maybe an effective model picture is what you're thinking about. So epilepsy doesn't exactly work like this, but for all intents and purposes, this is, a good working model that I can maybe make some predictions with. But of course you might, if it's really bad, you're just going to go and have to put more stuff in your model. Or maybe your theory is wrong. So what if you have only partial information or mixtures of information? Then you may have to incorporate a demixing matrix at the beginning of all this, or do ICA or something to split things up or reduce the dimensionality. And of course, it'll be a challenge to do this online during an experiment because it takes a while to fit, but this is not out of the question. Now, if I go back, let me just finish in 2-3 minutes here. So if I have data, I can estimate a model, and it could be, my favorite EI model, and I want to see if that applies to gamma rhythms or beta rhythms, and in particular, what regime are we talking about? So I didn't do it here. Okay, this is just properties of these regimes that look like gamma bursts. So what I'm showing here is a two-dimensional subspace of parameter space, the I to I coupling strength and the E to E coupling strength. And these ones are interesting because, in some models, for example, for Parkinson's, they'll set this parameter to 0, but in other models for Parkinson's, they'll set this parameter to 0. So we have both those parameters here. And there's a red curve here, which is the Hopf bifurcation curve, where you have a transition to synchrony. This is the Wilson-Cowan model with noise. It's not the Schwalger model. I'm going back to the beginning. I have a Wilson-Cowan model. And these regimes here, if you're moving closer and closer to the Hopf boundary, you go from this kind of, you get very rare bursts up to here where you get it's continuous, almost synchronous firing. So it turns out that these 2 points here are optimal in the sense of representing what we see in healthy data. And so what we've done, and I just want to mention some of this work because it's related to inference, is once you've inferred the parameters, you can maybe plug them in here and see if you're near a regime that reproduces the data. And burst statistics is yet another metric that you can use to see if your model makes sense. It's not just the spectral properties or the firing rates or so on, but you're looking at times between bursts and durations of bursts. It's like a higher level statistic that can help you constrain the model. And what we did is we can actually take the stochastic Wilson-Cowan model, apply a method known as stochastic averaging, and you get these equations for the envelope. If you want the Hilbert transform of the rhythm, the envelope, or the analytic signal envelope, and the phase. And these are 2 equations driven by diffusion noises. And they depend on all the parameters that you have in the problem. And I'm going to end here in 1 minute, is that it turns out that these parameters, D and nu, govern pretty much, and omega 0 govern pretty much all that's going on in a Wilson-Cowan model. They're going to give you the distribution of your envelope density. It depends on this parameter R, this meta parameter. And as you get closer and closer to the Hopf bifurcation, you're changing the burst statistics, and they just get longer and longer and longer. These bursts are longer and longer as you approach. So you can calibrate your model to see if you're at the right position. For example, you can calibrate this distance here to see if you're getting the right statistics. And what we also did is to calculated the mean duration of a burst, and this we formulated as a first passage time problem. And you can see the details in the paper. So the mean burst duration is approximately a sum of 2 first passage times, ones to go up and one to go down. And you can get some agreement with the data, from the numerical data and the theory, the red and the green lines here. So by extension, you can have a theory of rhythm bursts with stochastic averaging methods to produce envelopes, and you can find optimal regions in parameter space that look like the data, and you can use first passage time calculations to help compute these burst durations and see what parameters they depend on and how they can be corrected in the first pathology. And burst statistics also help to infer models. And I'll leave it at that. Thank you.
Great. Thanks, André, for this beautiful talk. I think this is very relevant to, to bridge the different scales in neuroscience. So I have a question from Suzanne. So at some point you showed the fit based on the meso model compared to the meso and the micro truth. It seems like the fit was better to the micro truth, even if fitted to the meso truth.
That's right. That's a very good eye. Yes, that does happen.
Okay. So the question is, was this just a coincidence in this specific case?
I think so. Like you're probably talking about this one up here. On this particular fluctuation, it does seem to be doing better. There's actually another example in here somewhere where we see it as well. Here, the spectral property of the inhibitory neuron population, it's fitting better to the micro. But yeah, good observation.
Funny observation, yes.
Total accident, I would say.
Okay. So maybe I will take the next question. At some point you showed, you're doing a Bayesian inference of your model parameters, right? And so you have your posterior distribution. In some cases, you have some ellipses, right? For WEI versus WII or something like this. So my question is, bug or feature? So you said, okay, maybe there's a feature to be, digged into the brain, but you can maybe also argue is maybe this is kind of a bug of the model or kind of an identifiability problem at this stage, right? So if it would be perfectly flat, it would be a signature of over-parameterization.
Yes, that could be going on partially. Given that we're only estimating half the parameters, the other ones are pinned, it's hard to know exactly what is going on. But these are, fairly, I would say, robust correlations that the model is picking out. I think what we would need to do is try it, for example, just pin these two parameters and relate them linearly and see how the model behaves and whether you can just do away with this. Same in this plot here when you have these very tight correlations.
Yes.
At this point, we were considering it a bug, an advantage. It might be overfitting. It's very hard to say what overfitting is in this particular context. I mean, we do have to run a lot of simulations to get, to find the map estimate. And and sometimes if we just don't have enough parameters, we can't find it.
Yes. And then maybe another question. So if I understood correctly, you have the micro model, you run it, and then you fit your meso model, right?
Yeah.
But it's like fitting based. Is there any chance of doing some kind of analytical calculations or computing some kind of a mean field way, analytically some effective model or something of this kind? Or you assume it already understand to be too complex in the micro such that it makes this enterprise just impossible from the start?
Well, let me clarify this. This model is a mean field model of the GLIF microscopic population. So although there's lots of boxes here,
yes, okay.
This produces analytically mesoscopic equations of motion for the mean activity of population 1, 2, 3, 4, 5.
You just still need to fit the parameters.
That's right. So, well, I mean, if you have, the theory tells you the connection of the parameters from the micro to the meso. You can read them off. Yes.
Right.
I mean,
Okay.
it's not completely transparent, but it's there.
I see.
So,
yes, of
so
course.
the theory
Yes.
connects them. So if your favorite theory, if you want to include, relax some hypotheses, include bursting or whatever else, if you have the theory to connect micro to meso, well, fit the meso and then work back from the theory to what the micro was. But yeah,
Okay.
this is completely analytic. Yeah.
Right. Okay, great. Sorry, I just missed that point. But,
no problem. Yeah.
Thanks for the clarification. Yes, so we're arriving at the end of this first parallel session on inferring models from data. I think this was very enjoyable, very different talks from the 4 different speakers. So I really want to thank the 4 speakers again. And now I'm sure everyone joins me in those virtual claps. So now